Welcome to the solutions for the Regents Motion in a Plane problem set, numbers 13 and 14. Let's jump right in with 13. Label important information here. We have a 615 kilogram, so that would be the car's mass, completes one lap in 14.3 seconds. That's time, around a circular track with a radius of 50 meters, and that would be little r. The car moves at constant speed. What is the acceleration of the car? And since it's traveling in a circular path, that would be centripetal acceleration. And what force, that would be F, must a track exert on the tires to produce this acceleration? Well, the force the track would exert on the tires would be the static friction between the tires and the track, keeping the car from sliding sideways. Okay? And if you have a question about why that's static friction, please ask about this in class. All right, the diagram, the circle that we have for a diagram here gives us a radius of 50 meters. Whoop. There we go. Radius of 50 meters. And let's just suppose the car is traveling around the circular track in that direction. Doesn't matter which direction we draw there. And it's doing that at constant speed. And they want the centripetal acceleration of the car. So let's start with A. We know centripetal acceleration from our reference table is v squared over r. Well, the problem in this question is that we don't know the constant speed. We're told that it's constant speed, but we don't know the value. Well, we do know that speed is distance over time, and we know that since the car travels one lap, so that's one time around the circle, that it travels a circumference of the circle, which would be 2 pi r, and it does that in a given time, which would be the period of revolution there. Okay, so that time up there is also the period, since it travels once around the track in that amount of time. Substituting 2 pi 50 meters in 14.3 seconds, we go ahead and calculate. Pause if you need time to do that. And we get a speed to 3 digits of 22.0 meters per second. We're now going to take that speed and substitute it into our centripetal acceleration calculation. So 22.0 meters per second. We have to square that and then divide by the radius of the circular path, 50 meters. So AC calculated, pause again if you need time, would be 9.65 meters per second squared. Okay? B, what force must the track exert on the tires? What we'll start off with here is Newton's second law. Summation of forces equals ma. Is the car accelerating? And the answer here is yes, because it's traveling in a circular path. It's centripetally accelerating. What force is causing the car to stay in a circular path? That would be the static friction between the tires and the pavement. So that's MAC. The mass of the car was given as 615 kilograms times our centripetal acceleration calculated in part A, 9.65 meters per second squared, multiply, and to 3 digits, we get an answer of 5,940 newtons. All right. So there's our force that the track exerts on the tires, and there's our centripetal acceleration asked for in part A. All right, in number 14, an athlete whirls a 7-kilogram hammer sorry about that. Athlete whirls a 7-kilogram hammer, that would be mass, tied to the end of a 1.3 meter chain in a horizontal circle. That 1.3 meters would become the radius of the circular path that the hammer travels in. The hammer makes 1 revolution in 1 second. This initially looks like time, but we also recognize with circular motion that 1 revolution in 1 second is the period of revolution. Okay? What is the centripetal acceleration of the hammer? AC. And what is the tension, capital T, in the chain? All right, once again, we start off with a little diagram here. We have our hammer, and this is as viewed from above, of 7 kilograms, traveling around in a circular path, radius 1.3 meters, and it does that in 1 second. All right, part A looks very similar to the last question. We have AC equals V squared over R. Once again, we recognize we don't have the speed, so we're going to go ahead and use our velocity equals distance over time, recognizing, once again, that's the circumference of the circular path divided by the period. So 2 pi times 1.3 meters over a period of 1 second. 2 pi times 1.3 to 3 digits is 8.17 meters per second. We now bring that back to our centripetal acceleration calculation. 8.17 meters per second. Square it. Divide by the radius of the circular path, 1.3 meters. Our answer has to be to 2 digits. And our centripetal acceleration calculated becomes 51 meters per second squared. Lastly, they want the tension in the chain. So for part B, again, we start with Newton's second law. Is the hammer accelerating? Yes, because it's traveling in a circular path. What force keeps the hammer traveling in a circular path? And that is the tension in the chain. Substituting, we have a mass of 7 kilograms, centripetal acceleration of 51 meters per second squared, and when we multiply, we get 360 newtons to 2 digits. All right, more to come on problems we'll do in class on centripetal motion.